Good morning, everyone. Today we're doing Unit 6, Lesson 3, Adding Vectors. So we're going to continue exploring vectors today. Over the next 2 days, we're going to look at what does it look like if we try to add two vectors together to ultimately get that resultant vector that we were looking at yesterday, or if we are going to subtract one vector from another to, again, get that resultant vector. We're going to create essentially that triangle and use some of our knowledge of trigonometry to find the magnitude and direction of these vectors. So two or more vectors can be added together to find a single vector called the resultant. We looked at the resultant a bit yesterday, and we'll continue to do so today and tomorrow. So vectors can be added by applying one vector after the other. Vectors are added using the head to tail method. I'm going to show you what that looks like here. So when we're trying to add two vectors together, not that you have to be spot on, but if you're going to be kind of meticulous about it, you would need to measure the angle, right? Because that's the direction and the length of a vector, and then try to translate it. So it says, consider the two vectors u and v. Find what u plus v would be. So I need to measure what u is. If I'm going to move it, I need to measure what it is so that I can move it over here. So I'm going to measure the length. And then we're going to translate it over here. So translate, which remember translate is just us sliding it to a different position. So translate with the same direction and same length. So I can't put a ruler up on the screen to show you guys this, but what I can do is, which is probably even easier, is I can just clip this direct vector and slide it over there. So let me see if I can do that. So I'm going to clip this vector, try to get it right at the tail so that it's the same size. Okay, so I've created this vector. I'm going to move it now so that the tail of it is at the head of the other vector. So it's that head to tail idea. If I move that right there, that's what that's going to look like. Okay, so I've now translated that. Let's see if I can write over top of. Right, I've translated that so that the tail of vector u is at the head of vector v. Now, the result of that is going to be a resultant vector. So if I go from the tail of one of those vectors to the head of the other, that is going to represent adding the two vectors together. So u plus v, which we're going to call our resultant. So the resultant vector. Okay, and this resultant is going to have a new magnitude and direction. Because remember, all the vectors are made up of a magnitude and a direction. So what did we do here above? We translated one of the vectors so that the tail touches the head of the other vector. And then we're going to find the sum by drawing and measuring the distance from the tail of one vector to the head of the other. And this is our resultant we're talking about here. That's that straight line segment we just drew from the tail of vector v to the head of vector u. So the new vector is the resultant, u plus v, which is the sum of vector u and vector v. Okay, so we're going to actually get in exploring how to do this. We're not going to do too much measuring for the sake of this curriculum. We're going to use more trigonometry, but that's the idea behind where those magnitude lengths come from. So let's look at different kind of vectors. So if we have parallel vectors, so remember parallel vectors are going to move in the same direction. So when you're adding two parallel vectors that are traveling in the same direction because they are parallel, the magnitude of the resultant vector is u plus v equal to the absolute value of each of those vectors. I'll show you what I mean by that with the drawing in a minute. And the direction, since they're going in the same direction, the direction is the same direction as u and v, right? No point in changing direction. They're both pointing in one way. They're going to continue to do so. So if I have these two vectors, again, and I'm trying to add them together, they're parallel vectors. They're running the same direction. They're never going to cross each other because they're parallel. I'm going to, again, do this by cutting this vector and translating it right next to u. I feel like it needs to go up a little more. There we go. Okay, so again, I just took this vector, measure, and translate, which is just slide. Okay, so the result of that is going to be our resultant. So if I measured the length of that, see if I can eyeball. So the resultant is simply going to be taking that u vector and adding to it that v vector. So that's our resultant. So that's the idea behind adding two things that are parallel. Since they're pointing in the same direction, we're just going to continue in that direction and add the two magnitudes together. Now, if we have parallel vectors that are moving in the opposite direction, so when adding two parallel vectors, u plus v, that are traveling in the opposite direction, where u is greater than v, so we're always going to kind of talk about this in terms of the bigger vector compared to the smaller vector. The magnitude of the resultant is going to be u plus v is equal to u minus the absolute value of v. Because you should think about, if it's pointing in the other direction, we're basically taking some magnitude away from the bigger vector. And I'll show you what I mean again with that with a diagram. So the direction is going to be the same as the larger vector. And we are referring to the larger vector as u. So think about when we add integers, right? When we add an integer where one is positive and one is negative, those are numbers working in opposite directions, right? The sign on the sum of those is always going to be whatever the sign of the bigger amount is. So let's look at one of these. So we have two parallel lines here again. So if I wanted to take the smaller vector, and I'm just gonna, oops. I'm just gonna think about translating that. So if I were to translate that on top of this vector, so you could see, oops. You can see that by putting the resultant on top of it, right, so we had u here, I'm just going to try to draw through there, and then we have v going the other way, then the resultant is going to be taking some of that magnitude away from you. So we're basically going to have a resultant that is the distance from here to here. Let's just draw our resultant over here. So the resultant is going to be basically that length there. That's the difference between the two. But it's going to keep the direction of the larger one, which is u, which was pointing to the right. And so we are basically taking our absolute value of u, whether that was positive or negative, and we're subtracting from that whatever the absolute value of v is. By taking the absolute value, we take out any signs and make sure that the larger of the two carries on the direction. Okay, direction vectors, or sorry, zero vectors, this should be no surprise. This is just like adding 0 to any integer. So the zero vectors has 0 magnitude and no specific direction. So adding two opposite vectors with equal magnitude results in a 0 vector. So what I mean by that is if we have a vector, let's say going to the right or moving to the right, and we will call it vector u. And then we have a vector going the opposite direction that has the exact same magnitude, right? Same magnitude there. Then when you add them together, v basically takes away all the magnitude of u. They essentially cancel each other out. They'll be u. Oh, sorry, it'll be 0. So some properties of addition. These also are no different than our regular properties of addition when we're adding vectors. So if we're talking about this in terms of 3 different vectors, so u, v, and w, the following basic properties will apply. So that commutative property, it says, if we do u plus vector v, that's the same as doing vector v plus vector u. Okay, so we can add in both ways. And I want us to think about this in terms of numbers. Let's say that u had a magnitude of 3 and v had a magnitude of 5. Well, wouldn't that be the same as saying 5 plus 3? No different there, right? Both are 8 no matter which way we add them. Another property that's always true is our associative property. So this is basically saying it doesn't matter the order in which we add numbers either. So this bracket forces us to add u plus v first, but if I stick the bracket somewhere else, say I leave u here, and then do v plus w, right? That bracket forces us to add the v plus w first. So order of addition doesn't matter. I'm going to use our same example there, throw in a value for our third vector. So what do we say up there? We said u was 3, v was 5. Let's say that w is 2. Okay, let's do it on the other side of the equal sign so you can see what I mean. So v was 5 and w was 2. So if I add my numbers on the left first, I have 3 plus 5 is 8, 8 plus 2 is 10. On the right hand side here, if I add my brackets first, that's 5 plus 2 is 7. Then add my 3, still 10. Doesn't change anything. The last property that's true is what we call our identity property. And our identity property is that when you add 0 to anything, it keeps its identity. So if we do u plus 0, still going to equal u. So no change when adding 0. Okay, the last thing I want to take a look at is let's look at a word problem in terms of setting up some vectors and then using this idea of trigonometry and adding vectors to solve for angles or side lengths that are being asked for in a question. So it says a boat sails 15 kilometers north 45 degrees west and then turns and travels 20 kilometers south 80 degrees west. So let's start with, I'm going to draw this down here just because I kind of know where it's going to land. Might seem kind of random where I'm drawing it. But let's start with our first vector here. Okay, so we'll say this is vector 1. So vector 1 is traveling along for 15 kilometers in a north 45 degrees west direction. So I know this is my north. Oops. And west is over here. So it's going 45 degrees. So I'm just going to start drawing that vector over here somewhere. Okay, I'm going to identify that it has a magnitude of 15 kilometers. And we also know that it has a direction north 45 degrees west. So this angle here is 45 degrees. Now at some point it's going to make a turn and travel another 20 kilometers south 80 degrees west. So let's call this vector 2. So at the end of 15 kilometers, it's going to make some kind of turn here. So we need a new compass here to identify that second vector. Whenever we're trying to identify a vector and it gives us a direction, we need to base that off of a compass. So it's going to make a turn and go southwest. We know this is south and this is west. So our vector should fall somewhere in this quadrant here, right? So now it's going to travel 20 kilometers southwest, and it's going in a direction of south 80 degrees west. And we know we're traveling 20 kilometers in this direction. Okay, and then we have some resultant that's going to connect those two vectors, which will show the displacement from one to the other. So let's take a look. So if I wanted to connect these two, first of all, let's stick arrowheads because we know we're moving northwest, and then we turn and we start going southwest, so we're going this way. So if we wanted to represent the resultant of that, we would start with a vector from the start of the first vector and draw it to the end of our second vector, okay? So it says, determine the angle the boat turned at between the legs of the journey. Okay, well, we can see where the boat turned. The boat came up here after 15 kilometers and made a turn. So the boat turned here. So we're trying to figure out that whole angle. So what's this angle here going to be? All right, so we have to learn what we have to use what we know about triangles. So we know that part of that angle is 80 degrees, but what about that other little part that's on the southeast side of that compass? So here's some things to think about. Remember what we know about alternate interior angles. So this 45-degree angle is going to create a Z pattern, right? It's going to create a Z pattern there. So that tells me that this angle here is 45 degrees. So then we can say that our total angle is going to be the sum of those. So 80 plus 45 equals 125 degrees. So therefore, the boat turned 125 degrees between the legs of the journey. Okay, it says determine the magnitude of the resultant vector. So now we need to figure out what is our resultant, right? So that's that vector connecting the start of our first vector to the head of our second vector. So we have to think about trig, right? What do we have here in terms of trig? Well, if I look at the triangle I've created here, I'm just going to draw it over here. Right, we're trying to find this side essentially. We know that this angle here is 125 degrees. We know that this side is 15 and this side is 20. Well, when I look at that, I have an oblique triangle. It's provided to me side, angle, side. So we're going to use our cosine law to determine that third side. So remember your pattern for cosine law. So it's going to be r squared is equal to, and then it's going to be the sum of the square of the other two sides. So that's 20 squared plus 15 squared, and then minus 2 times those sides. So 2 times 20 times 15. And that's all going to be multiplied by cosine of the angle that's related to the side we're trying to find. So 125 degrees is the angle opposite the resultant. So that's the cosine of 125. So if we calculate everything on the right there, we should find that r squared is equal to 969.145. And again, we don't want to round any of this until the end. So I'm just going to put all my numbers after my decimal. And then we solve for r by taking the square root of both sides. And we should find that r is equal to 31.1, and in this case we're talking about kilometers. So now it's asking us to determine the quadrant bearing of the resultant. So we're trying to figure out what is the quadrant bearing from the resultant. So remember that quadrant bearing is going to be determined from the beginning of that vector to the end of that vector. So if we look where our theta would be, well, our resultant starts at this vector and then moves in a northwest direction over here. So this is the bearing that the resultant creates. So that's the angle we're looking to find. So some information now we found in our triangle. If we just bring this triangle down here now, right, we're trying to find this theta here. We found that R is 31.1, this side's 15, 20, and this angle is 125 degrees. Well, if I need to find that theta, I have a side angle pair here, right, with 125 and 31. So I'm going to use sine law to find my angle. So we're going to take the sine of theta over its related side, which is 20, and set that equal to another ratio of sides and angles. So that would be the sine of 125 over 31.1. Then I'm going to multiply that 20 over to the other side so that I can work towards isolating theta. I'm going to have 20 times the sine of 125 over 31.1. We'll continue up here. And then finally I need to bring sine to the other side of the equation by taking the inverse. So the sine inverse of 20 times the sine of 125 all over 31.1. And theta is going to be equal to 32 degrees. Now we have to look at this. They want us to do a quadrant bearing, right? So if this part of our triangle, I'm going to go back to my original drawing, if this part of our triangle is 32 degrees, well, we need to know the quadrant bearing. The quadrant bearing is going to be from that north part of our compass, all the way to that resultant vector. So the quadrant bearing is going to need to add those two angles together, the 32 and that 45. So our quadrant bearing is going to equal 32 plus 45, which is 77. And then again, we need to look back at that original drawing and see what direction is it, okay? And we can see that we are northwest, so we would say that it's north 77 degrees west. Okay, so for both of those questions, we identified the magnitude of the resultant as 31.1 kilometers, and then the direction or the quadrant bearing of that resultant was north 77 degrees west. That's it for your notes for today.